Okay, so this is part 3 of section 4.1, and we're going to talk about linear independence. So I do want to recall the very last thing we talked about in part 2, and it's the superposition theorem for homogeneous equations. So if we have y1, y2, all the way to yn, our solutions to our homogeneous differential equation, then the linear combination y equals c1y1 plus c2y2 all the way to cn is also a solution. So we showed this pretty easily with the linear. Now I'm going to write down the definition of linear dependence and independence. So linear dependence. A set of functions, f1 to fn, are linearly dependent on an interval if and only if all the c1 to cn's are not all 0, such that when we have a linear combination, c1 f1 plus c2 f2 to cn fn, when it's equal to 0. So in other words, just like it sounds, linear dependence is when at least one function can be expressed as a linear combination of the others. So they are linearly independent on an interval if all the ci's in this equation are actually shown to be equal to 0. So our first example is just in general. If we have two functions that are linearly independent, they are linearly independent if and only if both constants are 0. c1 equals 0 and c2 is equal to 0 is the only solution to c1f plus c2g equals 0. Let's look at some actual examples. So we have two functions. So the set 4x plus a half and 16x plus 2. So it actually looks like these two are linear combinations of each other. So I'm going to say they are linearly dependent. And here's why. Since, well, it looks like if I take this equation f2 and multiply it by 4 f1 minus f2, I get 0. There's a linear combination. That's not c1 equals c2 equals 0. And we can check it. 4 times 4x plus a half minus. So we found a nonlinear, So we found a non-zero solution. So therefore it is linearly dependent. Again, like I said, they are linear combinations of each other. They're dependent on each other. So here we have 3 polynomials. We are missing constants in there, so my guess is they're dependent, but I'm not sure. So I'm going to actually set these up as a matrix. I'm going to write them out basically as function 1, function 2, function 3, like that. But we'll have our row of constants, our row of x's, and our row of x squareds. So our first function, f1, is just x. So there's a 1, 0, 0. There's no constant and there's no squared term in there. My second, x plus x squared, gets a 1, 1, and a 0 constant. My third one has 0, minus 3, 1. So setting this up as a matrix, if you've taken linear algebra, you should know that having a row of zeros is dependent. Okay, so this is in fact dependent. But now I'd like to show that it's dependent by showing that we can have a linear combination that's equal to 0, where all the coefficients are not all 0. So I'm going to look at, if I add these two together, well, I'll get 2x squared. But if I subtract it, so again, this is f1, this is f2, and f3. So if I take f2 minus f3, I have 4x, so minus 4f1, it looks like. And that's equal to 0, and let's check it. Minus 4 times x plus f2, x plus x squared, minus f3 is minus plus 3x minus x squared equals 0. The x squareds cancel. 3x plus x is 4x minus 4. I do in fact get 0 equals 0. So again, I found a non-zero linear combination. So therefore it's dependent. So this next example is going to be more in general, but it's going to lead us up to our next theorem. So C1f plus C2f. So here's usually what we're trying to solve to see if C1 equals C2 equals 0, it's linearly independent, or if there's a non-zero combination that's equal to this, it's dependent. So I'm going to actually take the derivative of both sides here. And what I have here is I've got a system of equations. So I'm going to write it like a linear algebra, like a matrix equation. And what we have here is my matrix is a 2 by 2, F1, F2, F1 prime, F2 prime. That's my A. My unknowns are my C1, C2. That's what we're trying to find. And my B is my 0, 0. So this is AX equals B. So what we have here is our B is 0. So AX is equal to 0. Where our X, like I said, is our unknown C1, C2. So some simple linear algebra that we can do to this is we can left multiply by A inverse if it exists. And if you remember, it exists if is non-zero, the determinant is non-zero, then I get x equal 0. Because any matrix times 0 is 0. So x equals 0 means my C1, C2 is equal to 0, which means C1 equals C2 equals 0, which is our criteria for linearly independent. So again, this is only linearly independent if and only if and only if A inverse exists, and that's if and only if the determinant of A is non-zero. Okay? So let's make this into a bigger case besides just 2 by 2, can go to n. And let's define the Wronskian. For a So this is this last example where we only had the first derivative. So it was a 2 by 2. If we have 3 functions, we need to make a 3 by 3 to find the determinant, and we'll have the first derivative and second derivative, including the original functions. Let's look at the previous examples we did. So the determinant, this minus that, is equal to since this is 0, therefore dependent. And that's what we got before. Next example. So this Wronskian, we get x squared. Well, this is certainly not equal to 0 as long as x doesn't equal to 0. If x equals 0, then we do have a dependent system. So we can say this is non-zero as long as x doesn't equal to 0, therefore this is independent. To set this one up by the definition, we had C1x plus C2x squared equals 0. We're trying to solve that. We're trying to find if there's a non-zero solution, if it's dependent. So we want to solve this. So we can choose values of x. We don't want to choose 0, of course. If x equals 1, we get C1 plus C2 equals 0. If x equals -1, we get minus C1 plus C2 equals 0, plugging it into there. And then actually we can solve this pretty easily just using algebra not linear. This is 2C2 equals 0. So C2 equals 0. It's okay for C2 to be 0. Then C1 has to equal to 0, plugging it back in. So that's, since we have C1 equals C2 equals 0, it's linearly independent by definition. So the Wronskian worked up there. So just in general, If the Wronskian's non-zero, then so basically what we just did and said was the theorem. If the Wronskian is non-zero, then this set of solutions are linearly independent. Okay? We proved it for the second order above, so you can use induction to prove. There's other ways to prove it too. It's true for the nth order. Let's do the other example, the last example that we haven't done. If I'm up there. You can use any row or any column. So you can use either 0, 2, 2 or x1, 0. I'm going to use x1, 0 as my cofactors. And when I cross off the x, that is the 2 by 2 that I get here. Plus 1 is my next cofunction, but let's be careful. If this is plus, this is minus, so we got to alternate that. And cross that off, and that's my 2 by 2 that's left. So calculate the determinants. So it looks like we do get 0. So if you get 0, it is linearly dependent. So it has to be non-zero to be independent. So here's a definition. I've highlighted the main parts. If we have a set of n linearly independent solutions of an nth order homogeneous, so if you have n solutions for an nth order and they're all solutions, then this is the fundamental set of solutions. Okay, so they have to be independent and they have to be solutions to be the fundamental set of solutions. It is equivalent so this is equivalent to linear algebra when you have n linearly independent vectors in Rn. So again, those numbers being the same n and Rn, they're independent. You have the right net amount, you have they're independent, and you have the same number of your dimension, then it forms a basis. So a basis is the same as fundamental set of solutions, just a different name. I'll probably call it both for a while. And that's going to be the same. So we have a fundamental set of solutions exist for a homogeneous nth order DE, linear. And that's the same in linear as a basis exists for any solution space. Again, what this means because it could be written as a linear combination, that our y1, y2 to yn are our building blocks for the general solution. So let's write out the theorem to find the general solution. So I'm not going to prove this, but it's proven in the notes. But everything that I've said basically led up to this. The big one being there's n solutions for an nth order. And of course, the superposition that at the beginning that we proved last time. You can see that comes into play here too. Let's do an example. So we're going to show quite a few things here. First, we're going to show that these y1 and y2 form the fundamental set of solutions. Then we're going to write the general solution. And last but not least, we're going to find a unique solution to the IVP. So part A, we want to show that y1 and y2 form the fundamental set of solutions. To be a set of the fundamental set of solutions, we need to show, one, that they are solutions, and two, that they're independent. Those are the two criteria in order to form the fundamental set. So let's show that y1 equals e to the minus x is a solution. We're going to be plugging it into the equation. So we need our first derivative and second derivative to plug in, and my second derivative. And then go ahead and plug those three in, y double prime. So 2 minus 2, yep, is a solution. And then my second one, e to the 2x. We're going to need our derivative and our second derivative to plug in. We're going to be plugging it into this equation. So 4 minus 4, we get 0 equals 0. Yep, that is a solution too. Which forms a true statement. So they are both solutions, but how do we know they are our fundamental solutions? They have to be independent. So these are both solutions. Now we need to prove that the solutions are independent. Remember, we add the exponents. So this doesn't equal to 0 for any value. So therefore, they are independent. So they're both solutions, they're both independent. It's degree 2, well, dimension 2, order 2. So therefore, so we found the fundamental set. Part B, the general solution. Since we found the fundamental set, all the work's been done for us. So our general solution is just a linear combination of the fundamental set with our two arbitrary constants. So now on to part C. We want to find the unique solution so since we have to use a general formula here because we're trying to find the C1, C2 using the initial value. So we want to use the initial values to find a unique solution using our general solution. So y of 0 equals 1, we can plug it into our general solution. E to the 0 is just 1. Now for the second one, where I prime of 0 equals 8, we do need to plug it into the derivative of our general solution. So we have to take the derivative. So plug it into there. And now we have our two equations, two unknowns. And we can use algebra 1 to solve it, or we can use linear algebra to solve it. I'm going to actually do it both ways to help those that haven't had linear algebra before. So two equations, two unknowns. I can just add, and the C1s will cancel. And then use this one to backtrack. And my particular solution is y equals minus 2 So we've done it. Now, I would like to do this using linear algebra to remind you guys how to use Cramer's rule. We did it on a previous video. And I'm pretty sure we need to know how to do it for a future solving differential equations of a higher order. So might as well learn it now. So this is my two equations, two unknowns. We change it to linear algebra using matrices. My matrix is 1, 1, minus 1, 2. My unknowns are my C1, C2 equals 1, 8. Again, this is my AX equals B. Cramer's rule basically says C1 equals A1 divided by the determinant of A, and C2 equals A2 divided by the determinant of A. So we can only use this if the determinant of A is non-zero. Let's find that first. Again, this is my A. My A1, we replace B, this one, with our first row for our A1. And the second row stays the same. So the determinant. So C1 equals A1, determinant of A1. Which is what we got before. And then A2, the determinant of A2, we replace B with column 2 and find the determinant. So C2 equals 9 divided by 3, which is 3. We got the same two constants. And it's the same particular solution. And that's it for this video.